So this will be 12 divided by 60. No? Okay, 1 is over here, right? And over here, if you take a look, this is 4 divided by 60. Which is,
12.
so that's what I did, put 12 divided by 60. Okay. Actually, in this example, the sum is also coming out to be 0, so it doesn't matter whether we put 16 over there or not. But anyway, so once again, if you have to create a special kind of high-pass filter, it could be based on a Gaussian low-pass filter, it could be based on a binomial low-pass filter. So all you have to do is identity, because identity is all pass. Subtract the two kernels and you'll come up with the high-pass filter, right? One more type of kernel. Yes.
Isn't the identity a diagonal form? So why is it only the second?
No, remember we discussed it in the last lecture for matrices. All diagonal ones is the identity. For images, because see, let's say you have 65, 80, 90, 30, 50, 40, 60, 20, 70, right, and so on. Okay, as we do the convolution with the kernel, okay, we want 50 to stay as 50. We want 40 to stay as 40. Okay, so if the kernel is 0, 0, 0, 0, 1, 0, 0, 0, 0, you'll see 65 times 0 is 0. All of these will become 0. 50 times 1 is 50, so the 50 will be maintained. Same way, if I move the kernel to the next set of numbers, 65, 73, 90, and the kernel moves over here now. So take a look, this will maintain the 40 as is, it will not change it. So the identity in image processing is when the center pixel is 1 for the kernel. But in matrices, it's the diagonal has to be 1.
Yeah.
Okay, so another kind of filter, very briefly, I wanted to show you is sharpening filter. And the way the sharpening filter works is, we basically, in plain English, it's the original image plus high-pass filtered image. So this is what we call the sharpened image. Okay, remember high-pass enhances the edges. Okay, so if we add it to the original, the effect is those edges will be slightly enhanced while preserving the complete original as is. Okay, so typically what we do is we define another parameter so that this will become, so S will become 1 minus P times the original image, but P times, so P is some parameter which controls the sharpening, which varies from 0 to 1. Okay, so this is our sharpening parameter. So for example, what will happen if I picked P equal to 1?
0. Half pass.
It will be just high pass. If I pick P equal to 0,
Just original.
just the original. So it gives us a nice control, right? Okay, so if we wanted to create this kind of kernel, as you can see, what we'll do is we'll do 1 minus P times 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay, plus P times. Okay, for example, let's pick one of the, when we did the original high pass with subtracting it from the 1, 1, 1. Remember, then it was what? Minus 1, minus 1, minus 1. 8 over 9. Okay, so this will be our sharpening kernel. So the sharpening kernel will come out to be, all of these will stay, let's see, 1 minus p, and so this will become minus p, minus p, minus p, minus p, minus p. Right? Now let's take a look at the center pixel over here. So the center pixel here is 1 minus p. Over here is
8p.
plus 8/9p.
Oh, okay.
Correct?
Yes.
So what will that? That will be equal to 1 minus p over 9, which is
over 9.
over 9. So if I put 9 minus p over here, and divided by 9 will be the kernel for the sharpening filter. So you can pick p. You can verify it easily if this derivation is correct. If we pick p equal to 1, right? Then what will this become? All negative ones, 8, which is same as the high pass. And if we pick p equal to 0, then this is center will become 1, which is same as the original. And in between you'll see. So in your next assignment you'll be programming this and applying it to images. I'll give you some starting code that you can, play with different kernels. Anyway, so that was the idea of the sharpening filter. So to summarize, okay, we have learned how to come up with a kernel given some kind of a frequency behavior requirement, like a low pass, high pass, and so on. Okay. So as far as filters are concerned, okay, they can be low pass, they can be high pass, they could be identity, as we had discussed, meaning doesn't do anything. Okay. And they could be band pass, meaning they pass a certain band of frequencies. So band pass frequency behavior will look something like this. Okay, certain frequencies will be allowed to go through, others will be blocked. Okay, so identity, hopefully you guys are very comfortable with it. Correct? Low pass, we further discussed 3 kinds of low pass filters. And what are those 3 kinds?
Average,
Average,
Gaussian,
low pass,
Average,
binomial,
Gaussian low pass,
Gaussian,
and
binomial.
binomial. All of them are doing convolution. So it's not like the kernel, once we come up with the kernel, we do a convolution with the original, right? So the average was 1, 1, 1, 1, 1, and all ones divided by 9. Gaussian, we discussed how you come up with the equation. Binomial, we discussed how you come up with the coefficients, right? And what was high pass? High pass was basically
1 minus
I is the identity, kernel, minus low pass filter kernel, correct? Because I identity produces all frequencies, so if we subtract it from the low pass, it gives us a high pass, correct? So again, you can plug in either the average or the Gaussian or the binomial to come up with the high pass kernel, right? So next one is the band pass filter. Okay, so what kind of, how do we create a band pass filter? So let me give you guys a hint.
low pass minus high pass.
Low pass minus a high pass, but it may end up canceling each other.
Cutoff frequencies must be different.
Cutoff frequencies must be different. So one way to accomplish this is create two low-pass filters with different cutoff frequencies. Okay. Now suppose somehow you're able to do this. Here's FC1. So this is LPF1. Here's another. This is LPF2. Okay. What will happen if I did LPF1 minus, or LPF2 minus LPF1? What will it produce?
FC1 and FC2 and band of
So it will produce something like this, correct? Now let me ask you this. Based on what you have learned so far in the lectures, which filter allows us to create or to move this cutoff frequency
Gaussian.
Gaussian? Okay, because remember, if I picked a certain sigma, either it will create a filter like this,
Or a wider filter.
or it will create a filter like this, correct? So if I subtract the two, it will create a sort of like a bandpass between the two. So the bandpass filter, popular choice over here is difference of Gaussians. Okay, so to come up with a kernel, what will you do? You'll pick some sigma 1, you'll pick some sigma 2. For example, this may be 1.8, this may be 0.9 or 0.6 or whatever. And then once you create a kernel for this one, then what do you have to do? Subtract the two values, just make sure the sum of all the kernel values is 1. Okay, so scale it if needed, and then you'll be done. So in your next assignment, you'll be programming a difference of Gaussian filter yourself, applying it to an image, and see what kind of effect it creates. Okay, so to summarize, these are, again, the very basic type of filters. Okay, so now we'll go into slightly more advanced filters, which are called derivative filters. So, okay, so remember derivative in the basic math, what does it mean? Once we take, if some function is given to you, and if we compute the derivative at a particular point, what does it tell us?
Slope, right?
The slope, or how fast is it changing? Okay. So in case of images, once again, if I, let's say this is some kind of a table, same color, if I did the derivative over here, what would you expect it to be? A two-dimensional derivative.
0.
Is there any change occurring between this and the neighbors?
No, it's going to be 0.
It's the same color.
So derivative is 0.
It will be derivative will be almost 0, right? If not exactly 0, if there's a slight bit of reflection of light or whatever, right? But what will be the derivative at this point?
There will be some value, right?
There will be some value. Okay. So one of the purposes of the derivative filters is, again, just like a high pass, to enhance the changes or to suppress the changes. Okay. But most of the time we enhance the changes. Okay, so these are based on first derivative and second derivative. So the two types of filters we have based on first derivative and second derivative filters. Okay, the first derivative filters are referred to as gradient filters. The popular filter, which is based on the second derivative, is called Laplacian filter. As we go along, we'll be using Laplacians sometimes, so it's important for us to not only intuitively understand it, but see how somebody comes up with a kernel for one of these filters. Okay, so let's say there's some pixel value p of xy. So this is the pixel value. Let me use a lowercase p, because as I mentioned in the pixel domain, it's like the time domain. Okay, so pretend that's a lowercase p. Okay, so if we are given some px, remember image is this is the x direction, this is the y direction. So any pixel value at a given xy could be 85, could be 112, right? So the way the gradient filter is computed is based on the first derivative, dp over dx square plus dp over dy square root. So this is the gradient filter. So essentially, as you can see, dp over dx is the derivative in the x direction, meaning how is the image changing in the x direction, how is the image changing in the y direction, and then once we square it, square root, essentially we are doing the average of how the change is occurring in both x and y directions, right? Okay, the Laplacian filter is basically based on the second derivative. Like I said, so this will be d square p over dx square plus d square p over dy square. So that's the Laplacian filter. Okay. So the question, before we come up with a kernel, what we need to do is essentially come up with how do we take the derivative in the pixel domain. Okay. Once we know how to take the derivative in the pixel domain, rest is piece of cake. Okay. So so the question is how to take the derivative.
Subtraction of the pixel values.
If both first and second derivative. Okay, so both first and second derivative. Okay, in the pixel. Okay, so there's a simple approach. There's a little more accurate approach. Okay, the simple approach, remember if you're given 2 points. Okay,
y2 minus 1.
let's say let me do it this way. Okay, so these are 2 neighboring pixels. Okay, if we know the value of the pixel here is 65, value of the pixel is 87 over here. So what will be the derivative at this point as an example?
y2 point minus y1 point.
Well, y in this case is really the pixel value.
Yeah.
So 87 minus 65. And what's the difference? How far away they are from each other? 1 pixel apart. So it will be simply 22, right? So that's a very simple derivative. We want a little more accurate derivative. So let me give you a little bit of a math refresher. Okay. So to compute derivatives more accurately, use Taylor series. Okay, so let me refresh your memory on the Taylor series. Okay, Taylor series has a couple of different variations, but the variation that we will use over here is strictly from the point of computing derivatives in the pixel domain. Okay, so the general formula for the Taylor series goes like this. If you're given some point x plus minus delta x, y plus minus delta x, sorry, delta y. Okay, so the idea is if you're given some point over here, you know the value of the function over here. So Taylor series helps us determine what will be the value of the function a little bit far away, where there's a certain delta x, there's a certain delta y involved. Okay, so if we know the value of the function here is known, okay, so at this point, let's pretend it's known. So the question is, what will be the value at this point? So delta x, delta y, small change in x, small change in y, Taylor series will give us a pretty decent approximation to that value. All right, so it goes like this. It goes as derivative with respect to x times delta x, derivative with respect to x plus delta y, derivative with respect to y plus 0.5 delta x squared over 2 d squared p over dx squared plus 0.5 delta y squared over 2 d squared p over dy squared plus third derivative, fourth derivative, and so on. Typically, we don't go beyond the second derivative. Okay. So once we have this Taylor series expansion or Taylor series approximation for the value of the function slightly away in terms of the original, and if we know the delta x, delta y, then we will use this to come up with the value of the derivative, the first order derivative, or the second order derivative, and so on. Okay, so we'll use the same approach as we did before when we were developing the kernel for the Gaussian. Okay, so if you take a look at a 3x3 grid as an example. Okay, so suppose this is 0, 0 again. This in terms of x and y. So this will be 1, 0. This will be minus 1, 0. Right? In terms of x, this is minus 1, 0, 1. Minus 1, 0, 1. In terms of y, this is 1. This is negative 1. This is 1. This is negative 1. This is negative 1. Okay, so this is basically the XY map. So given a center pixel, how the neighbors, so the delta x, delta y for the neighbors will be computed like this, right? So what we'll do is we'll develop 9 equations based on this neighborhood by applying the Taylor series formula. Okay, for the gradient filter, we will not use the second order terms. We will just restrict ourselves to the first order derivatives only. So this we will ignore for the gradient filters. Okay. So anyway, let's pick a point over here. So let's go to the left column over here. Okay, and write down these equations. Okay, so minus 1, so this will be p of x minus 1, and y plus 1. So delta x is minus 1 over here, delta y is 1 over here. Okay, So then what will this equal to? Delta x is
minus 1
minus 1
dx
dx plus
1 times
delta y is 1 dp over dy. Correct? Now let's go to the second equation. Second equation will be p of x minus 1 y. So this point over here, right? So x is minus 1, so minus 1 dp over dx plus 0 times dp over dy will be the equation at this point. Let's go to the third point. X minus 1, y minus 1, minus 1 dp over dx plus 1 dp over dy. Oh, sorry, minus 1. Minus 1. Okay, everybody okay with these three equations, right? Okay, so now let me add the three equations. So add these three equations. What will happen to the right side? This cancels.
First and last,
And then this will be dx. And this will be basically sum of pixels in left column. Everybody agrees? Right? Because aren't these basically adding these pixels in the left column? Okay. So very similarly, now let's go and take a look at the right column equations.
So we will have 3 times dp by dy. Just not over.
What's that?
We'll just have dp by dx.
Or dp over dx is basically some of these pixels in the left column divided by 3. So we have computed the derivative. Okay. With respect.
They were negative, right? Or can you figure out the sign?
Oh, negative. Thank you.
Oh.
Yeah, there's negative. Okay. So very similarly, let's take a look at the right column equations. Okay, for the right column equations, it will be p x plus 1, y plus 1 equal to 1 dp over dx plus 1 dp over dy. Then p
Of x.
x plus 1 y equal to 1 dp over dx plus 0 dp over dy, and the last equation is p of x plus 1 y minus 1 dp over dx minus 1 dp over dy.
3 times dp by dx.
So if we add these three equations, add the above three equations, so what will this come out?
3 times dp by dx.
So let me write down over here. Sum of right column pixels equal to this dp over dy cancels, right? 3 dp over dx. Okay, so once again from here we can say dp over dx equal to sum of right column pixels divided by 3, correct? So that's the conclusion from equation 2, meaning the right column. What was the conclusion from equation, the left column equations? So let me just call this equation 1. So if I rewrite this equation 1, so basically we are saying dp over dx equal to negative sum of left column pixels divided by 5. Okay, now let's combine this information together. If I add equation, so this was the rewrite of the equation 1. Add equation 1 and equation 2. So what would this become? 2 dp over dx equal to sum of right column pixels minus sum of left column pixels. Okay, divided by 3. And then, or I can take it over here, we can divide by 6. So now we have a very good approximation for the first order derivative in the x direction. Okay, if we take a look at this equation, as you can see, as far as the derivative in the x direction is concerned, does it have anything to do with the center column pixels?
No, it's
No.
0.
So the kernel for, yes, for dp over dx will be 0, 0, 0. Okay, and as long as these are equal but opposite in sign. Okay, so this could be, for example, negative 1, negative 1, negative 1, 1, 1, 1. Right? So this could be one possibility. Or if we wanted to pick binomial coefficients instead of 1, 1, 1, what was the size 3 binomial coefficients? 1, 2, 1. So then this will become 1, 2. So as long as they are equal. Okay. So this filter is a very famous filter called Sobel filter. Okay, so Sobel filter is basically, it uses the binomial coefficients. So it looks like this, and this is in the x direction. Okay, very similarly, I won't go through it, but to save time, see, I started with the left column and the right column over here. If I start with the top row and the bottom row and add the equations, I'll come up with the expression for the dp over dy. And once again, we'll basically see over here sum of top row columns minus the sum of bottom row columns, right? So the kernel for